Section 2 and Section 3 of this notebook are about the derivatives of vector functions. In Section 2, we study the algebraic computation. In Section 3, the geometrical aspect. The latter half of Section 3 will be a little bit too advanced for Calculus 1 level, so we'll probably end up skipping it altogether. In this video clip, we are going to cover Section 2 entirely and the first half of Section 3. Here we go. We begin with a vector function p of t, which is x of t comma y of t in case of 2D. If it is 3D, then we are going to need z of t as well. The method of computation is the same. We simply take the derivative of each component and put them together, x prime comma y prime. If necessary, z prime as well. Here are some derivation, but we are going to come back and talk about it after some example problems. Here we are. First example, we have my x as this function, and this is y. And we can take the derivative of each and put them together like this. Power function and exponential function. Easy. For this, we are using the product rule. Put them together and we have the final answer. By the way, this problem was simple enough that we can do it in a single step. Take the derivative of the first, we get this. Take the derivative of the second, using the product rule. Here we go. Which method do you prefer? My preference is solution 2, this one. But if you prefer the first one and break it down and do those derivative computation one at a time, please go ahead. It's a good way to reduce your mistakes if you're mistake prone. How about the next problem? Alright, this is my x and this is y. Both are composite functions, so we have to use chain rule. Here we go. This is x prime computation using the chain rule. And this is y prime computation, again the chain rule. Put them together, we have the final answer. How about this? Again, we can do them in a single step. The derivative of the first function, here we go, using the chain rule. The derivative of the second component, here we are, again by the chain rule. Solution 3, this is not really a separate solution, it's just a simplification, by the way. In the final form, please note that 2t plus 1 is common, so you can just take it out, factor it out, and then leave it as a scalar multiplication of this 2t plus 1 times the vector function. It's just a simplification. Which method do you prefer? As I said earlier, my preference is solution 2. You don't have to agree with me. If you prefer solution 1, go ahead. How about the next problem? Let's see, what is x and what is y in this case? Because this thing is a scalar multiplication. Well, this is what you're going to end up with. You can push this scalar multiplication into each component, and then what do you have? We have this product and we have that product. You can calculate the derivative of each using the product rule. Here we go. X prime computation using the product rule and y prime computation using the product rule. In the end, put them together. Here's solution 2. Push those t squared plus t inside, and then to take the derivative of the first component and take the derivative of the second component, put them together. This is solution 2. Solution 3, okay, a little bit warning here. Each time I talk about solution 3, some students will get a little bit confused. So if you think you are not really getting this, then please don't take too much attention here. If you are, inclined, then please go ahead, because this will turn out to be a useful tool in a little bit upper level mathematics, especially vector calculus, multivariable calculus, Math 2730. We are using the product rule where my first function u is a scalar and my second function v is a vector function. So this is my u prime, the derivative, times the second function, no change, u prime v, no change in v. Now this is u, no change, and then this is v prime, that's the derivative. So u prime v plus u v prime, that's the product rule. You can stop here if you want to, but I decided to put them together to get the final answer here, which are in line with all the other solutions. Which method do you prefer? My personal favorite is solution 3, and that'll turn out to be most useful in higher level mathematics. But if you're not getting it, forget it. There are 2 legitimate solutions already. Okay, so much for algebraic computation. Let's talk about some geometrical aspect of vector function. And here we go. The derivative vector, what does it mean? Actually, the definition of the derivative is, as usual, a Newton quotient. We have some algebraic manipulation here, p of a plus h minus p of a, so that's just subtraction. And then dividing by h is a scalar multiplication of 1 over h, basically. And this is the derivative vector. Now, what does it correspond to? It corresponds to this. F prime of a in one-dimensional case is basically this. And instead of this, we have f of a plus h minus f of a. And what is this quantity called? This quantity is called a Newton quotient or difference quotient. It represents the slope of secant line. Do you remember this? In case you don't remember, let me stop this recording and then get appropriate notebook here. Just give me a moment. Okay, I got the notebook here. And way back in week 3, we did this. We studied slope and tangency like this. Oh, not this one. Yes. Where y equals to f of x and slope of secant line is f of b minus f of a over b minus a, the change of y coordinate over change of x coordinate. And upon taking, oh no limit, if you take h as b minus a, then this is h, so it goes there, and b is a plus h. So we have this expression here, which we call Newton quotient. And that is the slope of secant line. And the next program here visualizes the approximation. Bunch of slope of secant line converging over to the slope of tangent line here as h gets smaller and smaller and smaller. Now let's go back to the vector function, and here is the visualization. We have a bunch of secant vectors converging into the tangent vector upon taking the limit. So this Newton quotient gives you all these secant vectors. Upon taking the limit, we get the derivative vector. What is the proof? Well, here is the proof as a matter of fact, and the proof is actually pretty simple. You see, here is a Newton quotient, and all you have to do is to push this algebraic computation into each component. Because this dividing by h is what? Scalar multiplication by 1 over h. So it just multiplies into each component. And then this addition, that applies to each component too. So in the end, we get the Newton quotient of x, Newton quotient of y. If we have one more component, then you're going to get a Newton quotient of z as well here. Now, upon taking the limit, what do you get? The limit of Newton quotient, hey, that's a derivative. Limit of a Newton quotient, that's a derivative. In the end, this is what we get. P prime is x prime comma y prime. If you have one more component z, then you're going to get z prime as well. So the proof is algebraic and pretty simple if you can reproduce it. And then the geometric meaning of it, here we go. We are looking at the tangent vector, which represents the velocity basically of this moving particle. Moving dot here, the red black dot is moving, and when it's moving more quickly, then the red arrow is longer. When it's moving more slowly, then this red arrow will be shorter. The direction, of course, will be always the same, the tangential direction. Here are more visualization associated to those, and this one is the simplest example, the line. Here's my function. If you take the derivative, what happens? X0 is constant, so that'll drop out, and the derivative will be derivative of ta. That's just a, isn't it? Same here. The derivative is b. So what do you get? We get a comma b. We have constant derivative. Not coincidentally, we have constant speed motion. Please note that this black dot is moving in the same speed. And then this red arrow on the blue line here, this one moving around, that has the same length. No change in velocity there. Now let me show you a little bit more general case. How about this ellipse case? Okay, I think this is a good one. Rotate it. Do you see the length of this arrow changing? Around this part, more flatter part, more quickly. The dot moves more quickly, and the red arrow is longer here. And around here and the other side, red arrow is shorter, and the dot moves more slowly. Please note the difference. And you can actually calculate the derivative pretty easily. x0 and y0 are constant, they're going to drop down, and you're going to get the derivative of this, negative a sine of t, and the derivative of that, we're going to get that. So this changes with respect to time t. Turns out that it's the longest around here and there, and then the shortest around here and there. Okay, so much for the ellipse. And then let's have some fun with some more aesthetically beautiful pictures. I named this curve as flower. I got it from our textbook, Stewart's textbook, but I thought this reminded me of a flower, so I named it as flower. I don't know whether that's really the right name or not. Anyway, please note that the length of this red arrow changes along with the speed of the black dot. When the black dot is moving more quickly, we get longer red arrow, and vice versa. Okay, another pretty picture. This one I made it myself. I didn't copy it from anywhere. And I named it Butterfly for an obvious reason. Again, let's make it slower. Please note that black dot is moving faster and slower. And then as it moves fast, we have longer red arrow and vice versa. So that's the visualization of the derivative vector.